Hello and welcome to Common Plastic Injection Molding Design Challenges, the Eccentric Injection Molding Parts Clinic, featuring our speakers, John Sidorowitz, Director of Customer Success, and Glenn Miller, Senior Tooling Engineer. John has been with Eccentric over 10 years, is a technically minded sales leader and problem solver in all things manufacturing. Having a degree in management and a very diverse background, John understands the entire manufacturing process from design to final product and everything in between. Glenn has worked for Eccentric for 3 years as a tooling engineer and quality control specialist. Prior to joining Eccentric, Glenn spent time as a CAD tool designer and tooling engineer with over 25 years in injection molding. This presentation is expected to last about an hour, and it is being recorded. We have 8 parts that John and Glenn are going to be reviewing, and we'll try to get through all of them in the allotted time. Please use the questions field on your screen to ask questions during the presentation, and our experts will address these throughout the webinar. We encourage you to follow Eccentric Mold and Engineering on LinkedIn so you can stay up to date on our latest blog topics and webinar schedules. And now turn over the webinar to our experts, John and Glenn.
Good afternoon, everyone. My name is John Sidorowitz. Thanks for the intro, Mark. Again, thanks for joining us this afternoon. Me and Glenn are going to kind of going through the agenda here. Sorry, I'm having a little technical difficulties getting some of these files up right now, so bear with me. But the agenda, we're going to go through 7 or so parts, display the part, describe its use, how it functions, and what it's used for, some of the challenges that we encountered or along the way, or point out certain features that are critical to the part and how we accomplish them, and just review them and review questions that you guys submit. And this is kind of open, so if you guys got questions as we're going through the parts, feel free to submit them, and we'll answer them as we go part to part, or we can always go back to certain parts and then just kind of rinse and repeat. So you have to just give me a second here. SolidWorks is still opening this one file. The first part we are going to be discussing, it's a overmolded handle. It's for a med device. It consists of a substrate and an overmold. And the green portion of the part is the substrate, which was an ABS, and the grayish was a TPE. Once I can get the file open here, we can kind of rotate around, but some key features with this was this was high use, so there was concerns of the rubber peeling off. So this part was made with mechanical holds in addition to chemical bonds between the two materials. And as you can see, we've got some critical shutoffs around the part. It was a smooth, seamless transition between the overmold and the rest of the part. So again,
that's really where the challenge is for the overmold, John, right? That's where we have that nice smooth handle, and the customer expects that to be seamless. And those areas are the toughest for shutting off the substrate part in the overmold tool. So that's something that we take a great deal of care in how we do that, and the critical nature of the substrate size is obvious. So the substrate has to be to the right size and has to be molded right to begin with. That way we get a nice fit in the tool, so we don't have a nasty rough edge on that seam.
All right, I'm finally getting somewhere with my SolidWorks, so I'm going to switch screens so we can hop over to this. All right, at this point, you guys should be able to see my screen. Glenn, can you confirm? I know
Yep, we're there.
All right, sounds good. All right, so we're just kind of showing the core half here. So I'm gonna kind of hide this so we can kind of see what's going on.
John, while you're doing that, we do have one question. Looks like the question is, was this a multi-cavity tool? It looks like you're seeing 2 there.
It's multi-cavity. It's actually a 1+1. So there's 2 mating parts, 2 halves to this handle. So we've got some, again, this is the Overmold tool. So there's some undercuts here along the outside of the part, and then matching ones on the inside of the mating part, in here. So the challenging thing with this one, as Glenn mentioned, was this seamless handoff or transition between the overmold and the substrate. As we all know, material has a shrink rate. Rubber materials more so than others, and filling this part and getting this material to shut off tight and clean against these edges, against a substrate that is going to have some variance to it. So it was really tight tolerance on the substrates, fitting that to the overmold tool, and getting a nice clean part for the end use doctor, nurse, whoever was using it.
The adhesion of the rubber overmold material to that substrate, it has to be nice and tight, fully packed out, full. The mechanical bonds that we're showing right there, the holes, all that has to be good. We don't want any of that peeling away afterwards, so it's definitely a challenge. Get that to fill perfect every time without any ratty edges, and it actually holds and adheres to the substrate.
Right.
Hey guys, we got a couple more questions. What are the materials that were used for both the substrate and the overmold?
This was an ABS, medical grade ABS, and I believe it was a VersaFlex, one of their OM materials for overmolding. So they have materials that are specifically made to bond with certain the matching material. So in this case, it was ABS polycarbonate.
Okay. Does the texture of the substrate pose challenge to fitment or shutoff?
No, it really shouldn't. Not really. The texture, a lot of times, especially on a part like this, it's a handle, it's a grip. So a lot of times the customer will want a texture or even a pattern on there, maybe some ribbed grip features, but no, that doesn't really pose a huge problem as far as the functionality.
Okay. I think you guys mentioned about adhesion, but someone asked what sort of adhesion was used, and I saw that you showed the holes in the substrate, as well as John, you mentioned the pairing of the 2 different materials.
So we've got these pass-throughs, or these holes that you kind of see through here. So these are creating mechanical bonds with the overmold material. So this part was actually subgated, so we're feeding material in through one of these holes, and then it will fill up in. So there's no gate vestige on the outside. It gives it a nice clean look. So as this part's filling, the material is going to flow back down into these holes and essentially lock in and create more surface area for the material to bond to. As far as the adhesion goes, it's actually in the material. There was no secondary process in between the substrate and the overmold where we put a primer or anything. The VersaFlex or the TPE material that we overmolded was made specifically to bond with the ABS substrate or an ABS material.
Next question is, does the clip system cause you to have a pullout? And what is that clip system called? You showed clips around the bottom.
These,
Yes.
I mean, we didn't need any actions or hand picks on the overmold tool because those were all formed on the substrate. I'm not sure what this clip, it's some sort of snap clip. I don't know if there's a specific name for it, but these would be created with actions on the substrate tool. So you would have a pull or a slide, on either side on this part, and then with the other one being on the interior of the part, here, you'd have internal pulls or lifters to create those.
Next question, did you need to marry cavity 1 sub to cavity 1 overmold, cavity 2 to cavity 2, etc.?
Well, in this case, this was low volume. So we only had single cavity. So the substrate tool was just a single cavity, and they matched up. So yeah, there was no concern of that. In a production setting where if you had multi-cavity, say it was a 2+2 or something like that, then yeah, you would probably want to match those up for the run.
All right. And another question, did you have to seal off on the core and cavity because of the holes coming through the ABS part?
Yes. So I think
Absolutely. Yeah, on the underside, the material will pass through those holes, as John said, through the substrate, and then it will shut off on the core side of the overmold tool. Now, whether they add a little pad there or it just simply shuts off on the curvature of the inside surface, that's how we get that to shut off in there.
yeah, so here is just a. So yeah, it was just basically a copy of the core side of the part, and just shut off on the inside. Okay. Let me switch screens here really quick.
Was SolidWorks plastic simulation used for part run or mold design?
No, not in. Yeah, we really don't use that. Let me close. I'm going to leave it open just in case we have want to go back. All right. Our next part, it's going to be a it's insert molded. It's not a metal insert. It's actually something flexible. It was a thermistor that's embedded inside this rubber piece. So let me switch screens again. So I really kind of just took it down to the bare bones. We've got the runner system. The cavity kind of forms this top section here, and little portions of it, but the kind of the meat and potatoes is, so this was a manual tool. Normally production setting, you would have these as slides, but this was low volume prototype. And so we have these two hand picks that form majority of the part. If I, so we can see what we're overmolding here, this thermistor. We didn't have much room or much to hold on to. We really had these two wires that are leading into the part. So we had to get creative with the gating, and there wasn't any special requirements as far as where this portion of the thermistor ended up. We knew we were going to get some flexibility because we had no way of holding it in here in the right position, or at least sealed in here, as long as it wasn't exposed. We were good. But this was a challenging part because there was a lot of playing around with the gate and to get that right.
Yeah, I mean, basically the using the two gates on opposing sides is in place so that we're trying to get a nice even flow, so they're not forcing that little substrate piece out of position at any point during the injection process. So that's what we developed here to keep that and maintain that in position. And as John said, that the larger end piece there, it was acceptable as long as it was fully embedded in the plastic and didn't show a short or a bleed through.
Right. Yeah, and this project was more so to prove out the design before it went to production, to see if it could be done, and then if it could be done in a production setting. Eventually, this did go to production with some changes, not with us, but I don't know if there's any questions on this one.
There weren't for this one, John, but there was a question that came in just as we were moving to this one. And the question is, what is the minimum wall thickness required when injection molding with silicone material?
I mean, we really don't run silicone. I'm not too familiar with it. Now, if we're talking like a similar, like a rubber type material, like a TPE, TPU, I mean, those are going to vary. And this part is pretty thick and chunky, as you can see. I forgot the exact material. I believe it was some special TPU with some fillers. But it's really going to depend on the material, and each material is going to have its own kind of wall thickness range that it likes. Typically 40 to 60 thousandths. I mean, this part by itself was roughly maybe 3/4 of an inch overall in height. From here down to here. So it wasn't a small part.
Right. I mean, in your wall thickness, it comes down to the particular material you're using. Some of these materials need to be pushed through the tool. Other materials, some of the rubber materials, kind of flow a little more like water. Not water, but will flow a little easier. So it really just comes down to the material itself and the application on how much the wall thickness should be.
Right.
And did you say you don't recall exactly what the materials were? The next question was what materials for the part?
Well, the purple is a thermistor, so it's like a off-the-shelf electrical component. So these are wire leads that are leading in, and whatever's going on inside here. I don't know anything about electrical, but so that was the substrate. And like I said, I believe the material was a TPU, but it was a custom TPU. It had electrical properties and fillers, so which allowed us to make a thicker than usual part.
And in this example, how much time did it take to develop the manual tool and run the first prototype?
I mean, this design, overall, we're probably looking at 15 business days. This is a pretty straightforward design overall, if you're just looking at the part. Like I said, the gating and getting that right may have taken a couple tries, but overall, the initial tool was about 3 weeks.
The whole purpose of running a tryout is to make adjustments as we go to see how the part's filling, see the reaction of the substrate as we're overmolding, and then just make slight adjustments to the gating system until we get it right. I mean, that's why you do a first shot, a little bit R&D there, trying to figure it out and fill it the best we can.
Yeah.
Question about temperature. Actually, we have two here. Did the temperature of the injection process need to be closely controlled in order not to not damage the electronic part?
In this case, I mean, this is an automotive component. I believe the OEM worked with a material supplier to kind of develop this material, and we just had to run it towards the spec or to the spec. So I don't really recall anything special or out of the ordinary for this one. But yeah, that would be a concern. Especially running, we've tried or overmolding circuit boards. You've got pressure and heat that you have to worry about. Typically, you want to go low pressure injection molding for something like that. But yeah, that would be a concern. So it's really going to come down to material and what you're overmolding.
Okay. The second question is the mold sometimes heated to provide better flow?
Yes.
Yes, I mean, you're gonna, molds will have to be heated or cooled depending on, to be a certain temperature for that material to cure and run properly.
Right, the manufacturer provides a range, and our head of molding runs our tryouts, and he will play within that range. Sometimes maybe go a little outside that to get a better fill and flow. It really just comes down to the particular part and wall thickness, and therefore there's a lot of variables that go into that.
Okay. And I believe that you mentioned this at the beginning about the challenge of the thermistor, but the question is, how was it held in place?
Let me switch back.
Really just hanging on to those rigid wires as a way to hold that in position. There really isn't any kind of mechanical hold within the part. As you can see, most of the part is that substrate part is embedded in the plastic, so we were able to hold it just on that outside.
Yeah,
there.
all you really had to hold was, this was the only, area the thermistor, excuse me, that was able to grab onto. So yeah, it was a matter of, trying to keep these as straight and the gates to flow around and get even pressure to keep this as straight as possible, during the injection process.
All right. Did you have any venting, and if so, where?
We really don't show it in here, but it's going to mainly be around parting lines, core cavity. So in this case, the main parting line was this line here around, and then obviously a split between the part down this length here.
Right. That's kind of what I was just going to say. It's kind of a natural opportunity there where all these split lines are, is provides us an opportunity to vent if need be.
Wrong screen there. All right, we may have to, I don't know why this part's not coming up correctly. May have to skip this part and go to the next one while I can pop it open.
All right, while you're doing that, we did have another question. Was injection speed fast to keep the insert position?
To be honest, it likely was not. We probably slowed it down a little bit, at least initially, to try and see how that component flexed or moved, and then made adjustments accordingly. The material sometimes dictates, the speed at which we are allowed to inject the plastic into the pool.
All right. So we're actually going to move on to this part. So this was a main body. It's actually for a tattoo machine. So it's busy. We've got a lot of core outs, undercuts, some threading, and insert molding. So let me switch screens here. So in this case, it was kind of built reverse. What typically would be the show side of the part is on the cavity side, but this was actually flipped around, and everything's buried in the core side. So what I'll do is, actually, I'm just gonna, you can kind of see how a portion of that's built there. Let me see if I can just, I had all these saved, and nope, I didn't want to do that. All right, that's what I want. So you can get an idea on how this part's developed. So we've got, a couple hand pulls. Well, actually, I think it ended up being 3 on this side. So that's an extra one. I don't know why that does that. So you've got 3 hand pulls or 3 actions that create, the thread area of the part, the sides, and a third that creates this core out with this radius here. If this radius wasn't here, we could probably pull it from, the other side, this pull, which you can kind of see down in here. And on this side, we've got an angled, let's try and move these components out of the way. You can see this pin is actually coming in at an angle, so that's another action. And then another hand pull that pulls in here. So this is a super low volume. Customer didn't want to move to a fully automated tool just due to cost, because it's kind of a specialty machine. And then we had a overmolded insert actually right here, which is this guy. So this is a very busy little part, and this part probably is roughly about 2.5–3 inches long.
As you can see there, We've got ejector pins down underneath of all the hand loads. So this entire assembly ejects out of the tool and then is manually demolded from there.
Yeah, which means no ejection on the part.
On the actual part itself, correct.
So and this was being handled by the tattoo artist. So parting lines were critical, and the placement of those. But most of the time, the way the part's designed will dictate where the parting lines are, how it's drafted and cored out. But in this case, it is kind of split down the middle here.
John, do you remember the question is, do you remember the cost of this tool?
Well, this is going back a few years. I mean, something like this right now is going to be, probably 11 to 12K plus.
And can you estimate what the part cost would be?
That's really going to depend on material, but it could be, anywhere $5 to $8, $5 to $9 a part, depending on material.
I mean, there's a lot going on here. There's a lot that happens after this comes out of the press. A lot for the operator to do, and then reassemble everything. So all that's factored into the cycle time, which kind of dictates piece price.
Yeah. So you can imagine, all these, pieces of metal come out with the tool or with the part. The operator has to manually remove them from the part, then reinsert them back into the tool, and then run the cycle through again. So that's a big price driver for piece price, which is, if you're looking at higher volumes, typically 1,000 pieces, 1,500 pieces or more per lot size, you want to look at automated tools if you have actions and can't get away from them. Now, if you're running lots of 100 or 50, a manual tool might be the cheaper route.
Was this all aluminum, or did you have some of the components that were steel?
This was all aluminum. I mean, the only thing that would really be steel is going to be this core pin. That's creating that, and the core pin that holds this, the metal insert. I mean, there's not really any crazy features. It's just busy. So.
Okay. I think you answered this question. Is the tool gun mold designed specifically for low volume production?
Yes.
You said it was. What type of heating was used, if any?
I mean, our heat, we've got a proprietary insert base system, so we do have heat, and it's usually water.
Next question, can a manual tool be turned into automated?
Maybe. Most of the time, no. Because depending on how the tool's built originally, you may not have enough room to automate or create slides within the tool. For instance, like this, if we want to automate this, it's completely changing the dynamic of the tool, and you would not have enough room to, create a slide and everything you need to do that. So, short answer is no. You want to do that up front.
This would have to be 4 times the size and really need some redesign to make that happen.
Right. And just because you can do it manually doesn't mean you can always do it automatic either, or easily. There's actually another part or a component to this assembly, which you've got two actions that are, one's dependent on the other and where that's at. So it basically one locks the other one in. And I flip back to the PDF, and hopefully I can get the CAD pulled up. We can kind of see that. So,
John, question that kind of builds off of that last one. Do you help the customer break down the manual tool option and the automated tool option concerning tooling and part costs?
Yes. Yeah, we can definitely do that. And that's really going to be driven by the customer and the quantities. So manual tool, cheaper, manual parts more expensive, and it's going to be flip-flop with an automated tool. So your automated tool is going to be a little bit more upfront cost, but your piece price is going to be much lower. So if you know that you're going to be running 2,500, 5,000 parts, something like that, the moving with the automated tool up front is just going to pay for itself in pretty much no time.
With regard to the hand loads, did you build duplicate sets that the operator could have prepped and ready to load?
We do that. Yeah, we do. It just depends on the situation, depends on the part. If we assume up front there's going to be a lot of wear, very fine details that could get easily damaged or wear out, yeah, we would consider, and that's for our team, you know, we would consider making duplicate pieces depending on the particular part, yes.
John, as you move on to the next part, the last question here is how much would this could be really design dependent, but how much would a manual tool cost be increased by designing it to be automatable?
It's really gonna, yeah, that's hard to answer. I mean, if you're talking a simple side action, you know, you could be talking anywhere from, you know, $1,000 to $1,500 to convert from a manual to a slide. But again, that's just putting a simple hole on like the side of a box. So it's really going to be design dependent.
What are some design considerations for molding when making microfluidic diagnostic prototype parts?
Let me read that one here. Oh, instead of making you say that again.
Yeah, thanks.
Yeah, I mean, that's I'm not too familiar with those type of parts, so that's going to be tough for me to answer. Now we may have some parts that are coming up that may resemble that, so maybe we can talk about those. Actually, the next part here is going to be an automated tool. So this is a type of snap fit lure medical component. Customer had really critical features, tight tolerances. Yeah, the seam line had to be pretty tight. And like I said, we ended up automating this tool because they actually wanted to mimic the production, you know, the full scale production, which was going to be either like a 32 or 64 cavity mold. So this is a pretty small part. It's probably maybe an inch plus long. Let me switch over screens here.
John, you said this is an automated tool?
Yes, right. It was.
Then we have a question that says, is the material of the manual tool different than an automated version?
Some components may be, you know, just because of the wear, maybe made out of steel. So yeah, that's.
In particular, like slide faces and things that are going to bear the brunt of the shutoff, we may potentially, you know, make those out of P20. It really depends on the situation.
Let me just color these really quick. So this one we can see we have two slides. I don't have the horn pins or anything in here, but you know, essentially, you know, as the mold opens, these sliders would move back, and you know, as you can see, the two parts here. We have our gate system that comes in. Actually, I don't know why this other gate system's in here, but the gate actually comes in through here and then feeds the two parts. And then there's a stripper plate below here that after, you know, everything's cooled, tool opens, stripper plate strips the parts off the core pins and parts fall out. So this is an example of you know, an automated tool. You know, parts fall out, these cycle back in, shut off on each other, and just repeat. So our main parting line is, roughly right here on the part. This would be embedded into the cavity side of the tool. These pins are actually a little bit longer, so they lock into the cavity side, so you don't get any sway during molding. Typically on parts, round parts like this, you want to have gates on each side to keep these pins straight and even. In this case, we only had one point gate right here on the side. So as you got to just imagine as pressure's hitting this core pin inside, it's going to want to push it towards the other side. Where if you have a gate on two sides, you got even pressures pushing on both sides, just kind of canceling it out. So we had to lock this pin in to the cavity side to keep it straight.
All right. Why did you use a stripper plate instead of a sleeve KO?
Simpler for manufacture.
Yeah.
It's just a plate with pins on the back side. That plate simply has that outer diameter wall stock on it, and we just push that plate straight up and it strips them both off. It's just a simpler design, easier to manufacture, more cost effective.
Did you need to cool the core pins to dissipate some heat?
We did not.
No.
There aren't any cooling directly at the core pins. No, there's not really enough room in the tool to add in any kind of cooling system through there. We put pretty simple cooling lines through the frames that John said are proprietary bases, and we generally just cool the entire mold all at once.
Yeah, and in this case, we're not running, at a normal production rate, of 10, 15 second cycle times. We're, something like this would probably be 25 to 35 seconds. So we've got ample cooling in between cycles. But yeah, we don't have any specific conformal cooling or within the tool. At least these tools. I mean, not to say we can't do it. We've done it with production type tools. But this one was a prototype to do a small scale mimic of the production tool.
Going back to the questions about manual versus automated, you said that manual tool often can't be automated because of size and features. How much would the cost increase to make a manual tool that is able to be converted to automated?
Well, then you're just talking real estate. That we'd have to calculate how much we would need potentially to have room for slides and other mechanics. So it really is just a footprint calculation, depends on the part size and so forth. So it'd be a per project, how we'd have to look at that.
Right.
Next question, great question. It goes to our core belief that this earlier you get us involved in your design, the better. This question is, how involved are you or can you be with supporting customers with their injection mold friendly design? Please give an overview of the process.
Well, I mean, our process starts with CAD. So if you have your CAD, you can submit it, through our website, through our portal, or get in touch with one of our account executives through, telephone, email. And what's going to happen is we'll take that CAD file. One of our application engineers will review it based upon, the project requirements, and develop a price based off of that. Now there may be conversations, in between that, if there's some parts or areas of the part that can't be made with molding, or maybe a different process might be better. But once there's a quote, you and the application engineer, along with the account executive, can basically review the quote, review, what could be done to lower costs, or what else could be done to the part to make it better. So it's really involved. You're not just submitting a part and just getting a quote back. Yeah, I mean, we're going to help as much as we can along the way to ensure you have a successful part coming out of that mold.
And like with anything, the more information the customer can provide us up front,
right,
as far as expectations, critical nature of the part, cosmetics, all of these things, then we can kind of help guide the customer to what they're actually looking for.
So how about material selection? The question is, how much are you able to help with selection of materials?
Good question. We don't consider ourselves material experts. I mean, we know enough. We can, suggest some basics. We do have a vast supplier base when it comes to materials, and access to material engineers that we can pair you with to nail down an exact material. If it gets past anything of, just need to be UV rated or UL rated in an ABS, I mean, that we can narrow down pretty quickly. But once we get into certain specifics, then that's where we want to bring in a material expert.
All right, next two questions are very similar. Are asking about, does the application engineer provide design for manufacturability feedback with regard to injection molding and the complete tool design? Also flow simulations.
I mean, what we do, I mean, we're doing a review of the part. They will put together a PowerPoint if there's issues, or we could just, hop on a Zoom call and walk through the part. We do a mold flow analysis. It's a kind of a low level, looking at fill, sink, pointing out thick areas, potential areas of non-fill. And then, again, just more upfront, the better we know about the project. That way we can, kind of, where we can't gate, what are the critical requirements of the part, the tolerances, all that's going to, be dictated by that. But yeah, we tried to do a full DFM and mold flow analysis on all the parts.
If I may just say, and the DFM, the mold flows, those are all wonderful simulation tools. Ultimately, though, it does come down to pushing plastic through this tool and actually seeing the results. And then once we do that, then we can make adjustments, make recommendations, maybe changes to improve the part, improve the fill, improve the entire process for molding.
So another great question along the lines of providing support. What's the typical turnaround for receiving that feedback and scheduling the call for project planning purposes?
I mean, typical quotes are turned around in 24 hours or less. If we have all the information. Now, if there is, if there are questions or we have file issues or anything like that we need to hop on a call, it could obviously take longer. But we try to turn around the quotes and feedback within 24 hours. Okay. So I've got this clip. So key features of this, it's got multiple actions. Just use some coring out and just how the part functions. It's got a mix of cosmetic and non-cosmetic areas, just the way how it's inserted, and just has some coring because there are some thick sections. So let's jump into this guy. There we go. All right, so this was another prototype tool, manual, so no slides or no automation. Let me just hide this. So actually, I'll just show this first. So we can see this is a very busy part in here. A lot of ribbing, cross sections, and through there. And we've got 3 actions total, one here, one back here, and one back here to create the part. And I just so this one's not too crazy. I mean, the only thing we had to do, being that this area of the part was cosmetic, but that's being captured by the cavity side, and the other exposed area is this this area in back here. So that's why it's pretty much embedded into this action here. So you would not see any seam lines, and the only seam line here, it's going to be, you know, kind of hidden in this rad. And this is where it mates to, you can just imagine a rectangular tube that this slides into, and this is exposed. And then this is the little snap feature that once it's in, and this would snap and pop back up. So we had some core outs here, some other mating areas. We gated on this end due to hide the gate, so we wouldn't have any gate vestiges on the outside of the part.
And again, this whole assembly with the hand loads all come out of the tool, ejected, and then has to be carefully demolded as to not, you know, damage the part during demolding or any of that. But yeah, it's a very slick design, a very interesting part. You know, sometimes we run into parts like this. It's an interesting. We don't see parts quite like this all the time, so it's always for us. We love the challenge. We love seeing new parts and new ways to do things.
We've got a couple of questions, not as specific to this part as they are to our general process. The first one is for color-specific parts, what sort of quality control is done to confirm color?
Well, I mean, there's a couple ways you can do color, and it's really going to depend on the project again. So if we're doing something low volume or prototype and it needs to be close, we'll do what we call salt and pepper. We will have a colorant generated to the Pantone that's needed, whatever that may be. You know, it could be your brand color. What we do is we'll send the material out and have a master batch of that colorant generated that goes along with the material. And then we mix that, you know, during molding. You know, it gets blended with the natural material, and the parts come out, you know, in color. It's easier that way. It's cheaper than going to a pre-colored, but it can lead to some issues. You may get swirling, much bigger parts. You can see some flow, uneven part to part coloring. So what we do is we have a swatch or a master plaque, which we use, that's approved by the customer, and that's what we use to check. But if you're running more production, you know, higher level, you know, or higher volume parts, you know, 500,000 plus, you do want to look at getting pre-colored materials. It's just going to be better overall, and it'd probably be cheaper at that point. You're just going to get better lot to lot and part to part consistency.
Right, and if you've got a customer that, and we have a couple that have multiple parts with us that all assemble together and form a unit, and they want, obviously they want consistent color across all the parts. They can't have 3 different shades of gray or blue. As John said, you know, if that's critical, it can be a battle using salt and pepper, and that's the point where we would suggest going to the pre-colored material to get that consistency that the customer wants. But again, that, as with anything else, it just really comes down to expectations from the customer and what they're looking for.
Yep.
As for prototype parts, do you do any first shot adjustments, or is that only for higher volumes?
Kind of depends on what adjustments we're talking about.
Yeah, I mean,
if
we're going to do
problem with the tool itself, then obviously we work through that during the tryout run. If there are any issues with the tool, some flash, we'll try to make those adjustments ourselves and get good parts. But again, it just kind of depends on what we're meaning by that.
Yeah. All right.
Last question, John, before you start on this one is, do you ever use electric heater cartridges in your tools? And what is your experience in this area versus using water? This is more a production tooling question rather than low volume tools we're reviewing.
Yeah, and we've used Cal rods in the past, which they're just really a pain to deal with. We've moved to a new kind of hybrid water oil. We really don't run a lot of hot tools. We can only get our tools max up to about 300 degrees. Anything higher than that, I mean, we're just really not set up for.
And that's running the water through an actual thermalator unit to pump the temperatures up even higher. So,
all right. There was a question, last question, and this was for part number 6. What were the challenges or unique aspects of that? If you could review those quickly.
Well, we did get a good part design. I mean, the customer did a good job of actually coring out, thick areas to minimize sink and things like that. It's a good part design. It's just, the nature of that one end to the right, no seam lines, so that dictated the design of that hand load. But yeah, there's areas there that are cosmetic, so different textures, different polishes. But other than that, I mean, it's still a fairly straightforward design, just putting it all together and getting that designed up. But that's what we do.
Yeah, I mean, there was some tweaking after. This was for an automotive application. We've got these kind of crush ribs here to finalize fit, and so they can figure out when they went to their production tool. So, I mean, it wasn't super challenging, but it's a busy little part. So yeah.
I think we've got time just to review part number 7 quickly.
Yeah, this one's so this is it's actually it's a 1+1, and this was actually built in the customer's custom, not really custom, but it's called a round mate, which we'll see in a second. It's similar to a mud tool, but round. These parts were unique in the sense they're medical type caps for like medicine bottles. Had internal threads and internal lock features, as you can kind of see. We've got these locks here. There's another lock back here, and some threads and undercuts throughout the inside of the part. We've got an undercut feature with this arrow on this back side on the outside of the part. Let me see, we can see the material there is polypro. So let's get into the tool. All right, so some of you may not be familiar with this. This is it's called a round mate. It's a tool that's round, and it kind of just snaps into a matching base. It's fairly interesting. So here's our parts. They actually wanted this to be a 2-cavity. The way we built it, for them, we were only running one side. The second was going to be for future use, in case they wanted to make changes. They can easily do that. This was a manual tool, as you can see. So we've got this loose piece here that's creating the outside arrow. And if I just pull this part out of here, we can start to see we've got 3 internal hand loads. So we've got 2 split lines that are actually going to be on the inside of the part. So when the part ejects, all 3 of these hand loads will come out at once. Let me hide this so you can kind of see. So imagine the part is, sitting on here. So what the operator has to do is essentially pull this first piece out, and there are undercuts on it. You can see here. It's polypro, so it is flexible. So it would strip out, so the part would be left like that. Then the operator would have to then push the hand load in and then pull out to capture this lock feature here, because this would not be strippable. Production setting, you'd have a lifter of some sort. And then the same goes for the other side. pushes in, falls out, and creates the other two lock features. And then put all three pieces of metal back together, put them back in the tool, and repeat.
And John, we've got a couple questions. They're more generic. One of these is, what's the availability for colored plastics? Can you get material in specific RL or Pantone colors? Or are there only a few shades of each color available?
You can get, if the material comes in natural, in its natural state, which most do, you can get it colored to any material. You can add a salt and pepper or have it pre-colored, where they'll just take it and dye it right at the machine that's making it. There are some materials that are out there that have set colors that they offer. There's some, like a Lustran 348 comes in a couple different colors. You've got, the natural white, black. I think there might be a red. So yeah, I mean, if the color of the material isn't black and it comes in some sort of natural variation of it, it can be colored.
Okay. Regarding this tool that we've got on the screen, so this is the question is, so a similar design is possible in an automatic tool?
Yes. It'd just be a much more complicated tool.
Lifters, all sorts of action. It would be very complicated. And
yeah, you would have to have this center area retract, or built in a way where the lifters clear that before. Yeah, it could be done, and it was done.
Yeah, if you're looking at the cross section of those three pieces, instead of straight walls, there'd be angles on there, so the center one could pull free while the other two pulled in as lifters and release those undercuts. So it'd just be a slightly different approach, but it is doable.
Yeah.
And you mentioned the second cavity was made in case the customer wanted to make changes, but only steel-safe changes could be possible after the mold tool is made?
Not necessarily. I mean, you can change out these inserts if they wanted to change the profile of something inside here. I don't remember, this tool goes back a few years. I don't remember the exact specifics, but I believe it was more so on the outside of the part, this area.
If they wanted to change the inscription or the call outs on there, they can do that. We could replace that piece. Various components can be swapped out and engineering changes done depending on the change.
All right, guys, our last question is with regard to sizing that Eccentric is capable of doing. And the question is, does Eccentric have any experience with large parts, 1 meter by 1 meter with low wall thicknesses, like 1.4 mil?
Not that big. I mean, our biggest footprint that we can run internally here is roughly 24 inch by 24 inch with a 5 inch depth, or like a 28 ounce shot size. We have partners here locally in Michigan that we can use and have used for bigger tools, but nothing that big.
Okay. Well, John, Glenn, thank you very much for, as always, a very informative webinar. Everyone, thank you very much for joining us today. We will send a link to the recording within 48 hours. And if you have any questions about today's topics, please email us at info@eccentricmold.com. Thanks and have a great day, everyone.
Thank you, everyone.